All right, so we're going to wrap up our chemical kinetics chapter, and we are going to talk about section 6. We're going to look at the collision model and energy diagrams and the Arrhenius equation. Okay, so in the collision model, we're going to be looking at, remember that this chapter is all about studying the factors that affect the rate of a reaction. And so far this chapter, we have looked at concentration and how that affects the rate of reaction. We've talked about catalyst and how that affects the rate of a reaction. So in this section, we're going to look at the temperature. And so we know this, that when we mix reactants together, those particles are in constant motion. And as they move around, they're going to collide with each other. And a fraction of those collisions result in products being produced. So again, I want to remind you that whenever we talk about things that are going to increase the rate of reaction, we need to talk about what are we going to do to increase the number of collisions that take place. So if we're going to increase the temperature, we have an increase in the kinetic energy of those particles, and that increases our number of collisions. All right, but again, only a small fraction of those collisions are going to produce a product. And so why does that happen? Well, there are actually two reasons that we're going to talk about in relation to the collision model. So the first has to do with activation energy. So when those particles collide, they have to meet a minimum or a threshold energy in order for them to break the bonds that are between the reactants and form new bonds to make the products. And we call this activation energy. So the symbol for activation is E of A. All right, so one of the things you would have seen, I'm hoping this is a review of first year chemistry, is energy diagrams. So this is the energy diagram of what happens when two NOBr molecules collide and how they produce NO and bromine as their products. So the change in energy, so delta E is referring to the difference in energy between the products and the reactants. So you can see delta E has been labeled on our energy diagram here. This has no effect on rate. Rate depends upon the activation energy. So you can see that the activation energy has also been labeled on our energy diagram. It's the difference in energy between the energy of the reactants and the peak of our graph. So this diagram, notice as you're moving from left to right across the x-axis, it's showing reaction progress. So you're going from reactants to the formation of products. Notice at the peak of this graph, you have a transition state. That transition state, that formation, is not a reactant or a product. Instead, it's this called an activated complex. So it's the state of what happens when we break the bonds between our reactants and we're forming bonds between our products. The other information we can gather from an energy diagram is if this reaction is endothermic or exothermic. So the one that's pictured here is exothermic. We can see in the graph that the products have a lower activation energy or a lower potential energy than the reactants have. If it's endothermic, then what we would see is that the reactants would have a lower potential energy than the products. All right, so this is a second energy diagram. And the one that we want to look at here is that this has two energy profiles on it. The green line represents an uncatalyzed reaction, and the purple line that's featured here has a catalyzed reaction. And you can see that in a catalyst, you're providing an energy pathway that has a lower activation energy. So again, the reason why catalysts are able to speed up a reaction is because it provides a path with a lower activation energy. So you're able to have more effective collisions because more of them are able to meet that minimum threshold energy. All right, so we can see by this graph that if we increase temperature, that we increase the number of effective collisions, and it increases exponentially. And we've seen this little k before. We know this lowercase k represents our rate constant. All right, and so here's our equation here. So we can actually calculate the number of collisions that would have an energy that would be equal to or greater than the activation energy at a specific temperature. So this lowercase e, you probably remember from math class, so that's the inverse of the natural log. It's equal to the negative E of A, so we know E of A is the activation energy. Now, we've seen R before. We know R is the universal gas constant, but in this chapter, it's going to have different units and a different numerical value. So here it's 8.3145, and it's joules per Kelvin times mole. And so since the temperature unit for the R constant is Kelvin, I want to remind you that your temperature units are also going to be in Kelvin. All right, so even though collisions may have enough energy, they still may not produce products. So what's the other factor that we need to take into account when we're talking about the collision model? And that has to do with orientation. So you can see again, here's my reaction of NOBr molecules to produce bromine and nitrogen monoxide. And you can see that not all collisions give me nitrogen monoxide molecules and a bromine molecule. So the other factor we need to account for in the collision model is molecular orientation. All right, so in order for collisions to be successful, the energy has to meet or exceed the activation energy when they collide. And the two molecules have to have a specific orientation in order to make products. Okay, so K we know is our rate constant. And then so we have some new variables here for us to talk about. So Z represents the collision frequency, okay, so how often they collide. P is the steric factor, which it's really telling us is the fraction of collisions that have effective orientation. And then sometimes in our equation, they'll combine the variables Z and P, and in that case, they refer to it as a frequency factor. And so we could rewrite the equation to look like this. All right, the last part of our notes we need to discuss is the Arrhenius equation. So if I take our equation that we just looked at with the rate constant and the number of effective collisions, and we want to get rid of this e to the power of negative EA over RT, we do that by taking the natural log of both sides. And so my rearranged equation looks like this. And it's really the equation of a line that matches this graph. So if a reaction obeys the Arrhenius equation, we can plot the natural log of the rate constant versus the inverse of the temperature, and it should give us a straight line. And so this is a version of the Arrhenius equation. Now, how we're really going to use the Arrhenius equation is we are going to use it to compare two temperatures. So we're going to look at that equation in a moment. All right, and the slope of the line gives us the ratio, it comes from the ratio of the negative of the net activation energy. So you can see that the line decreases over R, which is our universal gas constant. And then our y-intercept is the natural log of k. All right, so if rate constants obey the Arrhenius equation, this tells us that the collision model has to be reasonable. All right, so if we want to know the activation energy for a reaction, that involves us measuring. So we go in the lab, we measure the rate constant at several temperatures. And so this is the version of the Arrhenius equation we're going to use where we're comparing two temperatures. And so this is the equation I'm going to expect you to know for the test.